All right, so picture this. You are descending through about 3,000 feet.
Right into the thick of it.
Yeah, exactly. The weather is bouncing right at minimums. Your cockpit workload is just absolutely through the roof. And, you are already dealing with a degraded flight control system.
You're in alternate law at this point.
Right. You are flying in alternate law. You are scanning your instruments, running the checklists, managing the aircraft's energy. I mean, it is intense, but it is manageable, right?
Up until that one specific moment.
Right. And then you reach up and pull the landing gear lever down. And in an instant, the aircraft you were just flying fundamentally changes its entire identity.
It really does.
The safety nets just vanish. The handling characteristics aggressively shift. And the alarms start barking at you.
It's a massive shock to the system.
It is. So today's deep dive takes a stack of technical Airbus flight manuals, operational logic documents, and, raw simulator instructor notes to figure out the exact logic and the intense operational reality of what happens in that cockpit.
It's a critical safety of flight briefing, basically.
Exactly. We are looking at the automatic transition to direct law, the moment that landing gear extends.
And that is the perfect mindset to have for this scenario, honestly, because we are going to break down precisely what the aircraft is doing when those gear doors open.
Which is a lot.
Oh, yeah. But more importantly, we're getting into the critical engineering why behind it, because this specific transition, this exact split second in the flight deck, is really what separates the mere system managers from true aviators.
Okay, I like that distinction.
Yeah, I mean, a system manager can just monitor a computer, right? But a true aviator has to fly raw aerodynamics when the computer explicitly hands back the controls.
Wow. Okay, so let's unpack this. I am acting as the pilot here, and I just performed a simple mechanical action, right? I'm just dropping the wheels.
A standard procedural step.
Exactly. So why does the software decide to completely change its identity in response to that? Like, walk me through what happens the millisecond those doors open.
Well, the transition is immediate, and it's severe. If you are flying in alternate law and you command the landing gear to extend, the flight control computers automatically command a further degradation down to direct law.
Just automatically.
Yeah.
No way around it.
Right. It is a hardwired, unchangeable transition. And the immediate consequence of dropping into direct law is, well, it's a total loss of flight envelope protections. You are suddenly stripped of the invisible digital safety nets that normally keep the aircraft within safe aerodynamic limits.
Okay, before we get into the terrifying prospect of losing those safety nets, we should probably establish some baseline terminology for the listener.
Oh, yeah. Good idea.
Because you mentioned alternate law and direct law. For those of us who don't spend our days, casually reading Airbus systems manuals, what actually is a flight control law in this context?
Right. So a law is simply the software programming that dictates how much the flight control computers help you fly the airplane.
Okay, so it's the middleman between the stick and the wings.
Exactly. It defines the relationship between the pilot's hand on the side stick and the actual movement of the flight control surfaces on the wings and tail.
Got it.
So in normal law, the computer is essentially a highly protective co-pilot. It provides full autopilot capabilities, auto trim, and these hard limits that prevent you from flying dangerously.
So normal law is full protection. The computer will actively stop you from doing something foolish.
It absolutely will.
Yeah.
Now, if a system fails, the aircraft degrades to alternate law.
Which is where our scenario started.
Right. You lose some protections there, but the computer is still heavily involved in stabilizing your flight path.
Okay.
But direct law, which is what happens when the gear drops in our deep dive today, is exactly what it sounds like. It is a direct manual steering mode.
The computer just steps aside entirely.
Yes. The translation from your side stick to the flight controls becomes linear and raw.
Which brings us back to that sudden loss of protections. You said the safety nets just vanish.
They do.
What does that actually look like for the pilot in the seat? Like, what specific safety nets are we losing the moment the gear drops?
Well, you lose the big three. First, you lose alpha protection and alpha max.
Okay, and those are what exactly?
These are the systems that actively prevent the aircraft from stalling based on its angle of attack.
Okay.
So in normal law, if you pull the stick all the way back and just hold it there, the computer will only raise the nose to a safe maximum angle, that's alpha max, and it'll just refuse to go any further, keeping the plane flying.
But in direct law.
In direct law, that refusal is gone. If you pull the stick all the way back, the nose will just keep coming up until the wings lift entirely.
Wait, really? The aircraft will no longer actively prevent you from stalling? It will literally let you crash.
Exactly. It will let you stall it right out of the sky.
That is wild. Okay, what else?
Second, the bank angle limits disappear. Normally, the computer won't let you roll the aircraft past a certain extreme angle, usually around 67 degrees. In direct law, if you hold the stick to the side, the aircraft will happily roll itself entirely upside down.
Oh, man.
And third, you lose load factor protections. These are the limits that prevent you from pulling so many G-forces that you structurally damage the airframe.
Like bending the wings.
Right. The computer normally caps you at about 2.5 Gs. In direct law, you could theoretically pull the stick hard enough to snap the wings right off the plane.
So you are basically handed back full, unrestricted authority over a heavy commercial jet, for better or worse. There's no digital brain guarding the edges of the flight envelope anymore.
None. In place of those robust active protections, you are left with merely a velocity stall warning, or VSW.
So what does that do?
It is literally just an auditory alert. A voice in the cockpit will call out, "Stall, stall," but the system will not lift a single digital finger to stop you from doing it.
That is just a staggering amount of responsibility handed back to the pilot in an instant.
It really is. But you know what? The loss of envelope protections is actually only the first half of the shock to the system.
There's more.
Oh, yeah. The second, and arguably more immediately critical change for the pilot flying, is the loss of auto trim.
Wait, the auto trim function just dies?
It ceases to operate entirely.
Okay, break that down for me.
Well, in normal and alternate law, the aircraft is constantly trimming itself. If you command a specific flight path with the side stick, the computers adjust the horizontal stabilizer on the tail to maintain that path.
Right, so you can let go of the stick, and the plane essentially stays where you put it.
Exactly. But the second that gear drops and you hit direct law, that automatic stability is severed. Your main warning screen, the Electronic Centralized Aircraft Monitor, or ECAM, will immediately bark a red message at you.
And what does it say?
It says, "Use man pitch trim."
Okay, so it explicitly tells you to use manual pitch trim. You have to physically roll the trim wheels yourself to relieve the aerodynamic pressure on the stick.
Yep, you have to do it manually, just like pilots did 50 years ago.
I want to pause here because, this feels like a glaring contradiction.
How so?
Well, as an engineer, why would you deliberately design a system to intentionally strip away all stability and safety nets at the exact moment the pilot is closest to the ground?
I know, it sounds crazy.
You're maneuvering at low speeds. You're arguably most vulnerable to a loss of control. It just feels like the aircraft is betraying you right when you need it most.
It seems entirely counterintuitive on the surface, I completely agree. But we have to look at the operational why behind the design. And specifically, we have to talk about the flare mode dilemma.
The flare mode dilemma. Okay.
Yes. To understand why the engineers forced this degradation, you really have to understand what would happen if the computer didn't hand over control.
Okay, let's get into flare mode then. The flare is that maneuver you execute at the very bottom of the approach ramp. You pull the nose up just before touchdown to arrest your descent rate and let the wheels touch down smoothly.
Exactly. That is the maneuver. Now, think about how a fly-by-wire system operates. In standard normal law, you aren't actually moving the elevators when you move the stick.
You're not.
No, you are commanding a load factor. You are basically telling the computer, "Give me 1 G of flight."
Okay.
The computer then moves the flight surfaces to maintain that 1 G. But landing a trajectory-managed aircraft by commanding G forces feels incredibly unnatural to a pilot.
I can imagine. You don't land a plane by asking for Gs.
Right. You land it by feeling the aerodynamic sink and physically raising the nose to catch it.
So the engineers had to somehow bridge the gap between computer logic and human feel.
They did. Airbus engineers designed a specific subroutine called flare mode. At 50 feet above the ground, the flight control system smoothly blends into this mode.
Okay, what does that do?
It essentially memorizes the pitch attitude at 50 feet, and then artificial forces begin to gently push the nose down.
Wait, it pushes the nose down right before landing.
Yes, and because of that, to keep the aircraft flying level, or to flare for landing, the pilot is forced to progressively pull back on the stick.
Oh, I'm struggling to picture this.
Yeah.
So in normal law, the computer is essentially faking the physics of a normal plane so the pilot can land by feel.
That is a great way to put it, yeah. It artificially forces the pilot to provide continuous back pressure, simulating the conventional aerodynamic feel of an older aircraft entering ground effect.
Got it. It makes the highly automated jet land like a regular airplane.
Exactly.
But in our scenario, we aren't in normal law. We had some kind of failure earlier in the flight, and we are in alternate law.
Which is the crux of the entire engineering problem. Because you have degraded to alternate law, that artificial flare mode software is entirely unavailable.
It just isn't there.
Right. It cannot execute. So let us play out your scenario. Let's imagine the engineers allowed you to keep flying in alternate law with auto trim fully active all the way down to the runway.
Okay, so I am at 50 feet. I am in alternate law, and I start to pull back on the stick to flare the aircraft for touchdown. What does the computer do?
Well, the computer is still operating on load factor demand. When you pull back on the stick to flare, you are telling the computer, I want to change my flight path upwards. The computer agrees and begins to execute that command. But remember, a flare requires sustained back pressure.
Because I'm holding the nose up.
Exactly. The auto trim system senses this continuous pressure on your side stick and interprets it as a problem. It basically says, oh, the pilot is having to work too hard to maintain this new flight path. I should help.
Wait, if the auto trim tries to help while I am pulling back to flare, it's going to trim the nose up automatically.
It will aggressively roll in nose-up pitch trim to relieve the pressure on your side stick.
Oh, no.
Yeah, so you pull back to flare, and the aircraft automatically pitches the nose up even further for you.
So I'd realize the nose is coming up way too fast, and I'd relax my pressure on the stick to stop it.
But the horizontal stabilizer has already been trimmed nose up. The nose just keeps rising anyway.
So now I am ballooning into the air over the runway, and I have to push forward on the stick to fight the trim that the computer just rolled in.
And when you push forward, the computer senses sustained forward pressure, and the auto trim starts rolling in nose down trim to help you.
It's just a vicious cycle.
You would end up in a violent pilot-induced oscillation. You would be wrestling a machine that is actively trimming against your last command, overcorrecting in both directions.
That sounds like a nightmare.
The risk of a severe tail strike, dragging the tail across the concrete, or a total loss of pitch control at 10 feet off the ground is catastrophic. The computer, in its attempt to help you maintain a flight path, would effectively drive you into the runway.
Okay, here's where it gets really interesting. The computer is smart enough to know it is compromised.
Right.
It lacks the flare mode software, so it essentially fires itself before it can cause a crash.
That's exactly what it does.
It recognizes that automated stability during a flare without the specific flare mode logic is actively dangerous.
Yeah.
So by forcing direct law upon beer extension, which is the ultimate signal that you are committed to the landing, the system deliberately kills the auto trim.
It kills it entirely, and it is immediate and final for the duration of that flight. The engineers deliberately chose the lesser of two evils. Yes, dropping into direct law removes your protections and heavily increases your workload, but it guarantees that the side stick forces you feel during the flare directly correlate to the raw elevator deflection.
Okay, let's explicitly clarify that physical shift for the listener.
Yeah.
What does that actually mean for the hand holding the stick?
It means we are back to pure aerodynamics. There is no computer interpreting your load factor request. It is a direct mechanical to electrical to hydraulic relationship.
A one-on-one feel.
Yeah. Disabling the auto trim ensures that if you pull the stick back half an inch, the elevator moves a proportional amount and it stays there. You get back the conventional aerodynamic feel of the aircraft.
So you feel the actual weight of the air flowing over the control surfaces.
You do.
So in a twisted way, the aircraft abandoning you is actually the aircraft saving you.
That's one way to look at it, yes.
It forces you to fly raw, because raw flying is the only safe way to get the wheels on the ground when the digital brain is impaired.
The logic is flawless from an engineering perspective. But, flawless engineering logic often collides violently with human factors in the real world.
It always does, doesn't it?
Always. So having established why the engineers built it this way, we have to look at the messy reality of how actual flight crews handle this sudden, violent shift in stick sensitivity.
Yes. Let's step out of the textbook and into the simulator data. Our sources pull heavily from instructor notes regarding this specific gear drop transition.
Some really fascinating stuff in there.
Yeah, and from the data, this scenario is flagged as one of the most insidious traps crews face in training. Why is this specific moment so dangerous for a human pilot?
It really comes down to sensory overload and task saturation. Just put yourself in that seat. We set the stage earlier, right? Descending through 3,000 feet, bad weather, high workload.
Right.
You have already had a major systems failure to drop you into alternate law in the first place. You are incredibly busy running abnormal checklists, talking to air traffic control, calculating landing distances, and briefing the crew.
Your mental bandwidth is maxed out just managing the emergency. You are surviving the failure, not just flying a standard approach.
Exactly. And then you hit the marker, you call gear down.
And the bottom drops out.
The transition happens, the handling characteristics radically change, and the main warning screen barks that red command: use man pitch trim.
So what's the mistake pilots make?
The primary student error here, the trap that catches so many crews, is failing to anticipate the aerodynamic consequence of dropping the gear.
Okay, let's walk through a specific case study from the simulator gotchas.
Mm.
How does this error actually play out in real time?
Well, a very common scenario looks like this. The pilot calls for the gear, the wheels drop, the aircraft transitions to direct law, but the pilot's brain is still operating in alternate law.
They forget they just lost auto trim.
They forget completely. The aircraft slows down because of the drag from the landing gear, so the pilot adjusts the thrust levers, pushing them forward to add power and maintain speed.
Okay.
Or perhaps they ask the pilot monitoring for the next flap configuration, adding more lift.
Oh, I see where this is going. It sounds like pushing a heavy shopping cart from the very bottom rack instead of the handle.
Oh, that's a good comparison.
Right. If you apply power from underneath the center of gravity, the cart naturally wants to tilt up. Without auto trim to automatically correct for that, you bear the physical brunt of that physics.
That analogy perfectly illustrates the pitch and power coupling of an aircraft. In a conventional aircraft or in direct law, adding thrust under the wings creates a massive pitch-up moment.
The nose desperately wants to rise.
Yeah, and in normal law, the computer quietly trims that force away so you don't even feel it. But in direct law, the auto trim is dead.
The aircraft doesn't correct for it.
No, it doesn't. The nose rapidly pitches up.
And suddenly the pilot realizes their flight path is destabilizing.
And the physical side stick becomes incredibly heavy. Because the aircraft is out of trim, the pilot has to hold physical, sustained forward pressure on the side stick just to keep the nose from pointing at the sky.
That's got to be exhausting.
It is. If you don't rapidly reach down to the center pedestal and roll the manual pitch trim wheels, literally physically rolling a heavy wheel to adjust the tail surface and relieve that pressure, you will physically struggle to hold the pitch attitude.
You are fighting the aerodynamic forces of a 100-ton aircraft with your forearm.
And while you are wrestling this heavy stick, you are trying to process digital alarms, monitor your airspeed, and keep the runway in sight.
That's a massive spike in physical and mental workload.
It is. If a pilot is just reacting to the heavy stick at 1,500 feet, trying to muscle the aircraft back onto the glide path, they are already behind the jet.
So if the warning screen is barking at you,
Yeah.
and the stick feels like it's set in concrete because you changed thrust and forgot to trim, how does a pilot actually train to stay ahead of the aircraft? Like, how do you prepare for a system that actively strips away its own stability?
You cannot react to direct law. You must anticipate it.
Anticipate it.
The training focuses heavily on mental models. When you are briefing the approach earlier in the flight, the pilot must explicitly vocalize: when we drop the gear, we will be in direct law. I will lose auto trim. I will need to manually trim.
So it has to be a conscious, premeditated thought to build that mental muscle memory.
You have to prime your brain for the physical action before the computer demands it. The instructors in the simulator actually watch the pilot's right hand.
Really?
Yeah, if the pilot calls gear down and their hand immediately drops from the thrust levers to hover over the manual pitch trim wheels, the instructor knows the pilot is ahead of the airplane.
They're waiting to feel the pitch change so they can immediately trim it away.
Exactly. But if their hand stays on the thrust levers and they just stare at the primary flight display while the nose drifts and the stick gets heavy, they have fallen into the trap.
They're destabilizing the approach close to the ground because they forgot to fly the raw wing. Which brings us perfectly to the ultimate takeaways for you, the listener. Whether you are prepping for a simulator check ride, studying aircraft systems, or just trying to understand the extreme edges of aviation safety.
The golden rules.
Yes. Well, let's synthesize this operational reality into the golden rules for surviving the gear drop transition.
Well, the first rule is foundational to all of aviation, but it becomes hypercritical in this specific scenario. Golden rule number one: fly, navigate, communicate.
The classic trio.
Yes. When that gear comes down, you must internally acknowledge that you are no longer flying a protected, highly automated computer system. You are flying raw aerodynamics.
Your mindset must instantly shift from being a systems monitor to actively physically flying a conventional airplane.
Pitch and power, attitude and trim. If the warning screens are distracting you from keeping the aircraft stable, ignore the screens until the flight path is secure.
Fly the wing first. The computer is dead to you. Okay, what is the second rule?
Golden rule number two: anticipate your warnings and know your modes. Anticipation is your absolute lifeline here. You must expect the red "use man pitch trim" command before your hand ever touches that landing gear lever. You should be waiting for it.
You anticipate the pitch changes as the gear doors open and the drag increases.
Yes, you manually trim away the pressures on the side stick the exact second you feel them, and you fly the aircraft to the ground using raw skill.
So what does this all mean? I mean, we've dissected the software laws, we've looked at the aerodynamic realities of flare mode, and we've explored the physiological trap of a heavy side stick.
We covered a lot of ground.
We did. And it means that under the veneer of automated perfection, under the millions of lines of code and redundant fly-by-wire systems, gravity and aerodynamics always get the final say.
They absolutely do.
The system is designed to gracefully bow out when it knows it can no longer guarantee your safety, handing the ultimate responsibility back to human intuition and raw airmanship.
It is a profound design philosophy. The engineers acknowledge the limitation of the machine, and they trust the training of the human to bridge the gap.
Which leaves us with a fascinating and frankly a slightly terrifying thought to end on.
Oh, what's that?
Well, if these incredible flight control computers are explicitly designed to hand back manual control when they recognize their own critical limitations, like lacking a flare mode in a degraded state, what happens to safety as we push aggressively toward fully autonomous aviation?
That's a great question.
What happens when there is no pilot sitting there to take over the manual pitch trim wheel when the code reaches its aerodynamic limit? Are we designing systems that are eventually going to be too complex to fail safely?
Something to really mull over.
It is. Definitely something to think about the next time you hear that heavy clunk of the gear dropping beneath the floorboards. Keep your airspeed up and keep anticipating the jet.